Hello. This week again, we are gonna go through kinematics of a particle. So we will continue with curvilinear motions and how we are gonna solve in rectangular coordinates. Then after that, we will define the normal and tangential components of this kind of motion. Okay, let's state the general curvilinear motion. Curvilinear motion occurs when a particle moves along a curved path, such as, like we defined the straight line. If you have a particle and then if we have a curve, let's say we have a rod with a curve. So in this kind of motion, we have a curvilinear motion. Since this path is often described in 3 dimensions, vector analysis will be used to formulate it. The particle's position, velocity, and acceleration is given by the vector analysis. General aspects of curvilinear motions are discussed, and in subsequent sections we will consider 3 types of coordinate systems often used to analyze this motion, which is rectangular, right? So which is x, y, z, or I, y, j, rectangular, or normal and tangential. This is by linear coordinate. And then there is also polar coordinates we are gonna define with the cylindrical or polar coordinates, and we will end up with these curvilinear motions. The first variable is position. Position is considered a particle located at a point on a space curve defined by the path function, which is st. So it changed the position with time, is a function of time. Let's say position is a function of time, as we see here. The position of the particle measured from a fixed point O, which is here at the curve, the center, or wherever you will locate it, and will be designated by the position vector, which is r is equal to rt, which mean this particle, when it moves by time, which is st, right? The path is changing by time. The position places is also changing by time. When it changes, the r is also changed. So don't think this path is perfect circle. So that's why this r, our position vector, is changing by time as well. Notice that both the magnitude and direction of this vector will change as the particle moves along the curve. So if we have these guys here, we know the position or the direction is gonna go this way. But if our particle comes over here, it's gonna be normal to the y direction, right? Minus y direction, the direction. So direction is changing. Also, the magnitude of this vector is changing. Why? Because these guys is, as you see, the r is bigger than, let's say, r prime. So the magnitude is also changing. Let's see also displacement. Displacement is the differences between r and r prime, which is when the time change, the position is also changing. So there is the displacement, which is represented by delta s. Suppose that during a small time interval, which is delta t, the particle moves a distance delta s along the curve to a new position. defined by r prime, which is this guy, is equal to r plus delta r. We know that from the vector quantity, if we add each other, we will end up the summation of the vector, right? So this all is also a vector. So vector addition, we made it, and then we end up the r prime. The displacement delta r represents the change in the particle's position and is determined by vector subtraction, which is the delta r is equal to r prime, is a vector quantity, minus r, which is previous position. So if we subtract both of them with the vector quantity, we will have delta r, which is also a vector quantity. So we are gonna do here in this kind of motion vector algebra. After we finish up the position, let's jump to velocity, which is the one order of derivation, which we see here. The average velocity is the delta r over delta t. So it's during the time t, the average velocity of the particle is delta r over delta t, which is also the vector quantity, as you can see, the bold side. The instantaneous velocity is determined from this equation by letting delta t goes to 0, which is the limit we are going to take right now. And consequently, the direction of r, the displacement or the position, approaches the tangent to the curve. So it's the tangent to our r direction, right? So when we take the limit delta t goes to 0, delta r over delta t is represented by our velocity quantity, which is the first derivation of time and the position with respect to time. Since the delta r, dr will be tangent to the curve, the direction of v is also tangent to the curve, as usual. The magnitude of v, which is called the speed, and is obtained by realizing that the length of the straight line segment r in approaches the arc length delta s as delta t goes to 0. So we have v is equal to limit time delta t goes to 0 dr dt, which is delta t is equal to 0, which is the displacement over the time duration. Speed can be obtained by differentiating the path function s with respect to time, which is here ds over dt. So if we have s at the beginning, we say the path with respect to time. So if you take the first derivative with respect to time, it's giving our speed. And our last quantity is acceleration. Acceleration, if the particle has a velocity v at a time t, and the velocity v prime is equal to v plus delta v at t delta t, then the average acceleration of the particle during the time interval delta t is, as we see here, the average velocity, average acceleration is delta v, the vector quantity, over delta t, the time duration. Where we know that the delta v is v prime minus v. If we have the v at the time t and t plus delta t is v prime, then the subtraction of these two quantities is going to give us, which is delta v, which is the change of velocity. To study this time rate of change, the two velocity vectors are plotted such that their tails are located at the fixed point O and their arrowheads touch points on a curve as like position. Like if we take this again, the fixed point, if we have velocity, and due to the increase of the path, the velocity is also increasing or decreasing, whatever. So if we subtract, we will see the change of velocity with these 2 points. So the velocity curve, or like drawing this velocity term with a fixed point, is an imaginary, not like position, like real. So it's imaginary drawing a line. So this curve is called a hodograph, and when constructed, it describes the locus of points for the arrowhead of the velocity vector in the same manner of the path as describes the locus of points for the arrowhead of the position vector. So with this hodograph, and you take the again the limit time delta t is going to 0 dv dt, so which is again the derivation when delta t goes to 0. So the acceleration is equal to the first derivative of velocity or second derivative of position. So by definition of the derivative, acceleration x tangent to the hodograph, and in general it is not tangent to the path motion. So if we said like if there is path, and if we take the first derivative, it was the velocity, which is the tangent to the path curve. But if we take the second derivative, it means it's not anymore tangent to this path, but due to we are taking the first derivative with the hodograph, of course it's the tangent to this curve of hodograph. However, in order for the particle to follow any curve path, the directional change always swings the velocity vector towards the inside or concave side of the path, and therefore cannot remain tangent to the path. As we described the same thing as we are taking the second derivative, is not gonna be in the remain the tangent to the path. Like in brief summary, the velocity is always tangent to the path, but acceleration is always tangent to the hodograph. Okay, so the remarks is these guys. Okay, so if we take the derivative, is giving us the tangential line of this one. So in the normal path, the velocity is the tangent to the path. But if you take the imaginary graph, which is hodograph, if you take the first derivative of this velocity, it's gonna give the velocity curve is gonna give us acceleration, which is tangential to the hodograph. Okay, let's define our curvilinear motion in rectangular components. Then after that, we will jump to the other coordinate systems. But the easiest one, as we use the rectangular components, so let's start that. We will start some places because sometimes we cannot define the curve with rectangular quantity or coordinates. Motion of a particle can best be described along a path that can be expressed in terms of x, y, z coordinates, which is I, j, k in unit quantity of this x, y, z. The position, the first we need to define the position. If the particle is at point x, y, z as here on the curve path as you see the path of the curvilinear path, then its location is defined by the position vector, which is we plug in the ordinates as 0, 0, 0 x, y, z direction, and then we draw a straight line to the point x, y, z, which the particle is located at the certain time. So then after that we have a three coordinates, right? In IJK in units quantity. So we can describe as xi plus yj and zk in the vector quantity. So this is our path, the path of this curvilinear motion at a point. So we can describe x with a function of time, y function of time, and z as a function of time. And then we know that then therefore the path is a function of time. At any instant, the magnitude of r, the position, is, because this is all vector, so if we take the square of these magnitudes and add each other and then take the square root of it, we will end up the magnitude of the position, which is r. And if you want to find the unit vector of this guy, let's say as a u, as a unit vector of this path, so we need to do the position over the magnitude of this position is gonna give us that position's unit vector. For the velocity, the first time derivative of r with position is yields the velocity of the particle. So we know that the velocity is the r over dt, the first derivative. So we need to define x, like we need to take the derivative with respect to time for x, and then y with respect to time, and z with respect to time, the first derivative. Just because of the vector, so we separated to each terms. Then after that, we just need to make a chain rule. So xi, we know that we can take the first derivative first, then multiply by I, then plus, we need to take the x as a constant outside, and then we need to take the first derivative of the unit vector. We know that this is unit vector is constant, so with constant time, with taking the derivative of any unit is gonna give us 0. So this guy is gone. So dx over dt by unit vector is given by the each term. So it's gonna be dx over dt I, dy over dt j, dz over dt k is the final velocity component. So as we can show it, instead of dx over dt, we can show vx, which is the x direction velocity, y direction velocity, and z direction velocity. Or we can show x dot, which is x direction velocity, and y dot is y direction velocity, and z dot is z direction velocity. So this is all representation of short wave, and the magnitude of the velocity is given again the its vector quantity. So we can say x direction velocity square, y direction velocity square, and z direction velocity square of at each other and then take the square root is going to give us magnitude. For the direction, we say the velocity vector. Let's take the velocity vector, and if we divide it to the velocity magnitude here, is gonna give us the unit vector of the velocity component. This direction is always tangent to the path. We always say, if this guy is the path, if you take the derivative, is gonna be tangent to the curve. So that's why we say the direction is always tangent to the path. Lastly, we will analyze the acceleration in rectangular coordinates. So acceleration, as we said, the acceleration vector is the velocity vector's first derivative with respect to time. So is the x direction acceleration I, y direction acceleration j, z direction acceleration k. You can analyze same as the velocity component as previous slides. And then we can represent the x direction acceleration as the first derivative of x direction velocity, and x position second derivative, and y direction velocity's first derivative, or y position second derivative, or z direction acceleration is equal to z direction first derivative velocity of or the z positions double derivative. We know that we stated x and y and z depends on time, so we can take the derivatives. And acceleration magnitude is x direction acceleration square plus y direction acceleration square plus z direction acceleration square, and take all of their summations square root, giving us the magnitude. And if we want to find the unit vector of acceleration, we will take the acceleration vector over the magnitude of the acceleration, is giving us the acceleration unit vector. And we know that A will not be tangent to path, because we know that the path is tangent to the path is velocity, and we are going to take another another derivative. So this is not supposed to be a tangent to the path due to the second derivative of the time, or the first derivative of velocity. Before we go further, it's better to remind the chain rule because we are going to use in this class a lot. So in short, if we take a derivative of y with respect to time, which is for the first derivative, let's say, is dy dt. But if y given by x and x is given by t with respect to t function, so we can take this divided into two portions, which is dy dx and dx dt. As you see, if we multiply these two, it's gonna cancel each other, so it's gonna be again dy dt. So this is shortly is chain rule. Let's have an example, and then I think we can understand better. So if we take this y first derivative, we know that the y's first derivative is 3x squared, okay? Because we take the y with respect to x derivation, and we are going to take x first derivative with respect to time, so it's going to be x dot, right? So then after that it says x, what is x with respect to t, and we're just going to plug here t4 square, right? And the first derivative of x with respect to time is gonna be 4d cube. So if we take 3 multiplied 4 is gonna be 12, and this is t power of 4 multiplied by 2 is 2 power of 8, and we have also here 3, so we will end up t11, I guess, right? Yeah, 12 multiplied 11. If we take the second derivative, but if we take the first derivative, if we go through from the first derivative, we will have the same thing, and we just need to multiply, and it's going to be 133 t10, t power 10. So this is double derivative is easier way. Let's go to like double in derivative with using the chain rule. So we know that the first one is 3x square x dot. If I take the second derivative, this is the first derivatives, and I need to take the one more derivative. So I will base this guy, and then I will use the chain rule again. This is x squared, so it's gonna be 6x x dot. So I just take the first derivative, and then right now I will jump to the other one, which is I will make constant this guy 3x squared x double dot, right? So if I plug these guys here, and then I will end up again 132 T4. There's also here showing is gonna be 6 x dot x prime, because x squared, okay, x dot here, because x dot is coming from here, x dot is coming from here. And when we just plug instead of x t4 x dot 4t cube and x double dot 4 and 3 12t square, we will end up 132 t 10. You will apply and then you will see by yourself. Common example of curvilinear motion is motion of projectile motion, as we remember from our physics 1 class or high school class. Either is throwing from the horizontal places, or we are just dropping in the vertical sides, right? Or like we are pushing a horizontal or vertical, or with the aim, and then it just go in horizontal direction and vertical direction as well, but is showing a curved path. This guy is just gonna be free fall. If we are analyze the motion, we know that the velocity is v0, which is the initial velocity, and the acceleration multiplied by time is gonna give us the final velocity. We know that from our previous class. The position is the first position plus the initial velocity multiplied by time, and plus the acceleration times square of 1/2, the half of it. And the last one, we had the three equation. The last one is the velocity square. The final velocity square is equal to initial velocity square plus 2 multiplied by acceleration, the constant acceleration, of course, and final and initial position subtraction. So we know that this equation is valid only acceleration, if acceleration is constant, right? Where we are taking this one, if acceleration is constant, where the g is and the gravitational acceleration, which is constant, which we take 9.81 meter per second square. The first and last equations indicate that the horizontal component of velocity always remains constant during the motion, which is, as I said, the gravity, which is 9.81 meter per second square. For the horizontal, after we pass the horizontal motion, we just check it out the vertical motion. Vertical motion, we are taking the ay, the acceleration of motion in y direction, as minus g, and the velocity is gonna be, we are gonna apply here, so it's gonna be velocity of y is equal to v0y minus gt, and y position is equal to the initial position plus the initial velocity of y multiplied by t minus 1/2 gt square, and the final velocity of y direction square is equal to initial velocity of y square minus 2g y minus y0. If we go back to the horizontal motion, we need to apply the acceleration here in the horizontal part is 0, so we are just gonna apply 0 here. The in x direction velocity is just the initial velocity of x, then the x position is initial position plus the constant velocity multiplied by time in the x direction, the initial velocity, and again this guy and this guy is same. Our initial and final velocity in x direction is constant because there is no acceleration acting on. To summarize, problems involving the motion of a projectile can have at most three unknowns, since only three independent equations can be written. That is, one equation in the horizontal direction and two equations in the vertical direction, right? So we know that v0 is equal to v, and like the initial velocity is the final velocity. So it's one equation, and for the vertical one, we can have for the velocity terms two different equations. So a total of three equations we have, and once we get the x direction velocity and y direction velocity, the resultant velocity total v is obtained, and which is always tangent to the path, can be determined by the vector sum. As we see, if we know the vx and vy, we will add each other, and then we will find the vector quantity of velocity in x and y direction. Another coordinate system is normal and tangential components. We can take it. When the path along which a particle travels is known, then it's often convenient to describe the motion using normal and tangential coordinate axes, which act normal and tangent to the path, respectively, at the instant considered have their origin located at the particle. So if we take the O here and our O prime here, all right? So if we have a path located here, and if my particle is here, if I take again the origin over here, so the tangential coordinate is gonna give us the velocity. You know that if we take any fixed point, the tangent to the curve is gonna give us the velocity term, and then in this normal of the path is gonna give us the position vector. So that's why it's convenient to use this kind of terms. Is easy to describe this curvilinear motion, and also called planar motion. A particle moves in a plane along a fixed curve such that at a given instant it is at position S, measured from point O. So if we take these 2 points, we will have a distance S, a coordinate system that has its origin in the curve, and at the instant considered this origin happens to coincide with the location of the particle. The t-axis, which is tangent axis, is tangent to the curve at the point and is positive in the direction of increasing S. So we said that the origin is here and the position is going to increase, so the tangent of this t curve is positive in the increasing path, and we will designate this positive direction with the unit vector ut. And let's continue to describe. A unique choice for the normal axis can be made by noting that geometrically the curve is constructed from a series of differential arc segments, which is called ds. Each segment ds is formed from the arc of an associated circle having a radius of curvature r, which is rho, is represented by rho, and center of curvature O. Okay, so here, so at this point there is one rho, this point is gonna be another rho, so this is called radius of curvature for this curve. The normal axis n is perpendicular to t-axis. We just need to describe this t tangent to the curve, then the normal direction of this one is give us normal axis, and its positive sense directed towards the center of curvature O. So it's always be if we have a curve like this, it's gonna be inside, or if we have a curve like this, it's gonna be over here. The positive direction, like positive direction is gonna be here, is gonna be here for this kind of motion. Okay, will be designated by the unit vector ut. The plane which contains the n and t axis is related to the embracing or osculating plane, and in this case it is fixed in the plane of motion. All right, like these guys is the definition of this tangential and normal components. We are gonna solve many examples to understand this one. This is the definition of all this theoretical part of the dynamics. Let's see how we are gonna define the velocity term in normal and tangential components. So particle moves in the s is a function of time, and particles velocity v is the, if we take the path, is the tangential, or of course and also it's called v, has a direction that is always tangential to the path, and a magnitude that is determined by taking the time derivative of the path function as t, right? So which is like the time derivative ds dt. We know that the velocity of this vector quantity is the velocity or speed multiplied by the ut, which is tangent to this curve. And the velocity, this velocity magnitude, we know that if we take the path first derivative, it's gonna give us v, which is speed, also like it's called, right? The magnitude of velocity, let's call it the magnitude of velocity. So if we take the first derivative, the path is gonna give us the magnitude of the velocity. If we multiply by the tangential curve, we know that the velocity is always tangent to the curve. We will find the velocity in normal and tangential coordinates. And for the acceleration terms, in acceleration terms, the v is a little bit complicated, but let's define step by step. So the acceleration of the particle is the time rate of change of the velocity, which is, remember, is tangent to the path. In order to determine the time derivative, which is u dot t, note that particle moves along the arc ds, which is the here, right? In time dt, then ut preserves the unit vector of tangential preserves its magnitude of unity. However, its direction changes and becomes u prime tangential direction. So u prime tangential direction is the unit vector of tangential plus dut, which is the derivation of the, or the infinitesimal change, which is here, right? So when it changed the time, the velocity in the curve changing from here to here, right? Because this is the tangential for this point, but when it comes to this point, it's changed the direction. So we need to take into account this one. We know that the ut, the unit vector, is equal to the magnitude is 1, right? So dut has a magnitude. Dut is 1 multiplied by d theta, because it's changing by the theta. It's a little bit too much theoretical, but just like try to understand. If not, just like focus on the formulas, which is giving you the better understanding here is the more physics going on inside, because when we change the ut to u prime t, our theta direction coordinates is changing with delta t, which is infinitesimal part, like the tangential part is changing by the delta t. So it's also defined by the un, right? dut is equal to d theta un in the normal direction. So it becomes ut prime, ut dot, the first derivative of tangential unit vector is equal to theta dot, which is the theta, like the change of angles, the first derivative with the normal direction, normal unit vector. Also, we say theta. We know that since this radius of curvature, we take this radius of curvature is equal to ds. The path is rho d theta. Theta dot is equal to s dot, which is the function of time, over rho. So at the end, we just need to remember this term. If we want to take the first derivative with the tangential unit vector with respect to time, is theta dot un, which is s dot over radius of curvature multiplied by normal direction unit vector. S dot, we know that is the velocity magnitude. So when we come to our finalized acceleration term, acceleration is v dot, which is v and the velocity magnitude's first derivative multiplied by the tangential velocity unit vector plus v multiplied by u time the tangential velocity's unit vector's first derivative. Let's go back how we are come up this one. We know that v is equal to v ut, so we are gonna take the multiplication rule. The first term's derivative multiplied by second term is constant, plus the first term is gonna be constant, then multiplied by the second term's derivation is gonna be here, as you see here. Then we know that v dot is the acceleration, right? Acceleration in the tangential term, ut, and v ut is gonna be, we are gonna change it in this term, which is v square over rho un, which is normal acceleration term multiplied by the unit vector of normal direction. So if we summarize it, u prime in like the unit vector of tangential unit vector first derivative is v over rho, the normal unit vector. Then acceleration is the tangential acceleration multiplied by tangential unit vector plus normal acceleration magnitude multiplied by the normal unit vector. And we need to define at is the first derivative of velocity, and an, the normal direction acceleration, is v square over rho, which is radius of curvature. The radius of curvature is given by rho is equal to 1 plus dy over dx square power of 3 over 3 over the second derivative of y with respect to x. This is just given, it's a mathematical form, we don't need to go through the whole details. And if we want to use this term, we know that ads is equal to vdv, but we need to use this term for the tangential acceleration term. And if we want to take the acceleration magnitude, is again is a magnitude like vector quantity. So we need to take tangential acceleration squared plus normal acceleration squared, and all of theirs square root, giving us the magnitude of acceleration. To better understand these results, if the particle moves along a straight line, then radius of curvature goes to infinity. And if it goes to infinity, the normal acceleration goes to 0, right? And thus, acceleration is gonna be only the tangential acceleration, which is dv dt. And we can conclude that the tangential component of acceleration represents the time rate of change in the magnitude of the velocity when it is a straight line. But what we are doing right now is a curvilinear motion, which is curved path. If the particle moves along a curve with a constant speed, then the tangential acceleration goes to 0. We know that if the velocity is constant, the acceleration is 0, right? But in curvilinear motion, tangential acceleration is 0, but the normal acceleration is not 0, because you are gonna take the velocity square over the radius of curvature in order to find the normal acceleration. So therefore, normal components of acceleration represent the time rate of change in the direction of the velocity in curve. Okay. Since the normal acceleration always acts towards the center of curvature, it's sometimes referred to as the centripetal or center-seeking acceleration. Let's solve two examples in order to understand this concept better. We will go through after this couple of weeks, when we finish up all this kinematics part, I will make a review and I will solve more questions. But right now, in order to understand the previous one, I will just solve two questions we will depict. Then I'm gonna end up for this week. Alright, for the first example, let's write our question. A boat travels around a circular path, which is the radius of curvature is rho is equal to 40 meters at a speed that increases with time, and v is equal to 0.0625 t square is the velocity function. The question is asking find the magnitudes of the boat's velocity and acceleration at the instant t is equal to 10 seconds. Alright. So, as in our subject is a curvilinear motion, and velocity is given by the time function of time, which is velocity is equal to 0.0625 t square, and we are gonna find the magnitude and then the magnitude of both velocity and acceleration. All right. So the velocity we know is the magnitude of velocity, right, multiplied by the tangential direction, ut, tangential direction of unit vector. With a time at t is equal to 10 seconds, we just plug it there. The velocity is equal to 0.0625 10 square, which is 100. So it is 6.25 meter per second. So this one is meter per second. Here is also meter per second. It's like the units is given. Let's consider it. Acceleration, we are gonna take the acceleration. We know that acceleration is the tangential side of acceleration, which tangential plus the normal side acceleration with multiplied by unit normal, and it is velocities, the first derivative of velocity multiplied by ut plus, we said, velocities, the magnitude of velocity square over radius of curvature. This is normal unit vector. And if we take the first derivative, the velocity's first derivative, here let's take the first derivative, we just need to multiply by 2, which is 0.125 t, right? And if we take the first one, is gonna be meter per second square. So at again time 10 at t is equal to t is equal to 10 seconds. We just need to plug, which is v prime is here 0.125 t. When we multiply by 10 is gonna be 1.25. The acceleration is 1.25 ut, which is tangential unit vector, plus v square. We know that v is 6.25, so we are gonna say 6.25 square over, which is radius of curvature is 40 meter, so we are gonna divide 40. This is gonna give us the normal unit vector. So at the end, our acceleration is gonna be 1.25 ut plus 0.9766 un. All right, so we found our acceleration vector. So we are gonna find the magnitudes of both velocity and acceleration. The velocity, we already said the velocity is the ut. Velocity at 10 is 6.25. So the velocity magnitude is gonna be by itself. So it's gonna be 6.25 meter per second. So acceleration, I need to square root of 1.25 square, which is tangential direction acceleration square plus 0.9766, which is normal side acceleration square. When I add each other and then take the square root, I will find 1.59 meter per second square is gonna be our acceleration magnitude. So we both find the magnitude of velocity and acceleration at instant t is equal to 10 seconds. For the second example, let's write again the question. A car travels along the road with a speed of v is equal to 2s, which is the path. So it's gonna be meter per second, the unit, where s is in meters and rho, which is radius of curvature, is 50 meters here. All right, and what is asking? Find the magnitudes of the car's acceleration at s is equal to 10 meters. All right, here velocity is given with the function of s, which is 2s. All right. So we know that is a curvilinear motion. So v is equal to the magnitude of velocity multiplied by the tangential unit vector at position, which is s is equal to 10 meters. We just directly substitute it for here. So the velocity vector is gonna be 20 in the tangential direction, 20 meter per second in tangential direction. All right. So right now we need to find the again acceleration term, which is the tangential direction acceleration with tangential vector plus again the normal direction acceleration multiplied by the normal unit normal. As again acceleration is the velocity derivative multiplied by the ut and v square, the magnitude of velocity over the radius of curvature un, which is a normal unit, and this is tangential unit. Here is the acceleration. So if we want to take the velocity with respect to time, because this is the velocity derivative with respect to time, what do we need to do? We need to use the chain rule, right? Which is dv dt, this guy, which is dv I want to represent by the ds, and ds dt, I know that ds dt is velocity, so it's gonna be velocity and velocity's derivation with respect to s. So I will multiply these guys, let me divide it here. Velocity is gonna be 2s, and I will take the derivative with 2s is 2, so it's gonna be 4s is gonna be my velocity's derivative. So at s equal to 10 meter, the velocity derivative, which is acceleration, tangential acceleration, is gonna be 4s, 4 multiplied 10 is gonna be 40 meter per second square. All right, so I will edit each other. So it's gonna be acceleration is, I know that the velocity's first derivative is gonna be 40 and unit tangent direction plus v square, which is v, we define here v is 20 20 the velocity is at s is equal to 10, we just need to plug here, is going to be 20 square, which is 400, right? 20 square over 50, which is radius of curvature, the normal direction. 400 over 50 is gonna be 8 meter per second. Here is, this guy is 8 meter per second. So the acceleration, the vector quantity is gonna be 40 in the tangential direction and 8 in the normal direction. So un and meter per second square is a vector quantity of the acceleration. If you want to find the velocity magnitude in s is equal to 10, it's gonna be only 20, because it only has, the velocity is only has tangential direction. So if you take the square and then take the back, it's gonna be the same thing, 20 meter per second. But in acceleration, we have two directions, so we need to make the vector addition. So 40 square plus 8 square, to take it their square root, is gonna give us 40.8 meter per second square. All right, that's it. So as you see, we can solve if we have the time function or the position function of the velocity given. So we can find with using normal and tangential direction and solve all this question easily. All right, this week is done. Thank you.